Inside that phone you're probably holding right now, there's this tiny, unsung hero working around the clock to keep everything running. Seriously, most people have never even heard of it, but without it, your phone would be a useless brick. It's called an LDO, and we're about to dig into its surprisingly fascinating story. But first, let me ask you something you've probably wondered about. How is it that your phone works just as flawlessly when the battery is at 10% as it does when it's fully charged at 100%? Well, the answer to that question points to a massive engineering problem that every single battery-powered device has to solve. In this visual right here, it shows you the core problem perfectly. As you use your phone, right, the battery's voltage just naturally drops. It's unavoidable. But, and this is a big but, the super important parts, like the processor, they are incredibly fussy. They demand a perfectly stable, rock-solid voltage to work right. So how in the world do you bridge that gap? Okay, so here's the journey we're going to take to figure this out. We'll start with the basic problem of unstable power. Then we'll meet a legendary but flawed old hero. After that, we'll see the revolution it sparked, explore a tiny city of regulators inside your phone, witness the ultimate team-up, and finally, we'll peek into the future to see what's next. All right, first up, let's tackle that big question. How do our gadgets actually deal with this unstable, dwindling energy coming from a battery? Well, the whole secret lies in a component called a voltage regulator.
So what even is a voltage regulator? The best analogy is a dam. A dam makes sure that the water flowing out of it is always at a constant, controlled level, right? It doesn't matter if the reservoir behind it is overflowing or nearly empty. A voltage regulator does the exact same thing, but for electricity.
And what's really cool is that there are kind of two main philosophies or teams when it comes to building these things. You've got the linear regulator, who's like a purist. It gives you this incredibly clean, quiet, perfect power, but it's super inefficient and just wastes a ton of energy as heat. Then you have the switching regulator. It's the pragmatist. It's crazy efficient, like over 90%, and runs cool, but its power output is electrically noisy and it's way more complex. It's a classic engineering trade-off.
Now, to really understand our modern hero, the LDO, we've got to go back in time and meet its ancestor. This is the story of a truly legendary component, the 7005, and its tragic flaw. I mean, it's really hard to overstate how big a deal this little three-legged chip was. Before the 7005 came along, getting a stable 5-volt supply for your electronics project was a huge pain. This thing made it literally plug and play. It completely democratized electronics, letting pretty much anyone build stable circuits easily. But for all its greatness, it had this one fatal flaw, especially as the world started moving towards portable battery-powered devices. It was just terribly inefficient. The 7085 basically turned a huge chunk of your precious battery power into useless heat. Anyone who's used one remembers needing this giant chunk of aluminum, a heatsink, just to keep it from overheating. And the reason for all that wasted heat? It boils down to this one really crucial concept: dropout voltage. The best way to think about it is like the minimum headroom the regulator needs to operate. It's the smallest possible voltage difference between what goes in and what comes out, for it to still do its job. So here's the problem in a nutshell. The classic 7805 had a massive dropout voltage of about 2 volts. That meant to get a stable 5 volts out, you had to constantly feed it at least 7 volts. That entire 2-volt difference was just pure wasted energy, converted directly into heat. Not great for a battery. And this right here is the aha moment. Just look at that difference. A modern LDO, which stands for low dropout regulator, slashed that required headroom from 2 whole volts all the way down to as little as 0.1 volts. This wasn't just a small improvement, it was a total game changer that basically made the mobile revolution possible. So how on earth did engineers pull off this incredible feat? Well, that brings us to the low dropout revolution. The real magic happened deep inside the chip. Engineers completely ripped out and redesigned the internal valve that controls the flow of electricity. They tossed the old, power-hungry transistor design and swapped it with a much more modern and efficient one, like something called a PNP or a MOSFET. It's like they took out a gas-guzzling V8 engine and dropped in a hyper-efficient modern one. But even with that new engine, there were choices to make. This is a fantastic analogy for the engineering battle that happened inside the chip. With one type of transistor, the PMOS, it was like having a big, powerful truck. Strong and simple, but also a bit big and slow to respond. The other option, the NMOS, was like a nimble little sports car, way smaller, faster, and more responsive. Now, that sports car seemed like the obvious winner, right? But it had this one really weird quirk. To fully turn on, it needed a control voltage that was actually higher than the battery's own voltage. So how do you solve an impossible problem like that? Well, engineers came up with a brilliant hack. They built a tiny voltage booster, called a charge pump, right inside the chip itself. It's kind of like building a mini oil refinery inside your car just to make the special high-octane fuel it needs. Just absolutely clever stuff.
Okay, so we've got this amazing, super efficient little component. Now let's see how it all comes together in the device you're holding in your hand right now. Welcome to what I like to call the tiny city of regulators. Get this. Your smartphone doesn't just have one or two of these LDOs. It has a single master power chip called a PMIC, a Power Management Integrated Circuit. And inside that one chip, there can be 20 to 30 individual LDOs all working together. And it's not just a random jumble of them. No, each LDO is a specialist with a very specific job. You've got one dedicated to providing ultra-clean power to the sensitive camera sensor. Another one is in charge of low-noise power for your audio circuits. A third one is making sure the phone's radios get perfectly stable power. And they're all digitally controlled by the main CPU, turning on and off in milliseconds to save every last bit of energy.
But hold on a second. You might be thinking, hey, didn't you say linear regulators, like LDOs, are inefficient? So why on earth would you use 30 of them? And that is a great question. This brings us to the final and most clever part of the story, the ultimate power team-up.
Okay, this is where it all clicks into place. Engineers decided to combine the two types of regulators we met at the start. So first, an ultra-efficient switching regulator, a buck converter, does all the heavy lifting. It takes the, say, 3.8 volts from the battery and efficiently knocks it down to maybe 1.3 volts. It's super efficient, but the power is a little noisy. Then, that slightly messy 1.3 volts is fed into an LDO, and the LDO only has to do this tiny final polish, dropping it from 1.3 to a perfectly clean 1.1 volts for the processor. And here's the kicker. Because that voltage drop is now tiny, just 0.2 volts, the LDO itself is also incredibly efficient. It is truly the best of both worlds. This amazing hybrid system is pretty much the state-of-the-art in every phone today. But you know how it is in engineering, the challenges never, ever stop. So what's coming next? I mean, we've just seen this incredible evolution. We went from a simple, hot but revolutionary three-legged chip all the way to a sophisticated, intelligent city of hybrid regulators all working together on a single piece of silicon. The pace of this innovation has been absolutely relentless. And that really leaves us with a final big question. As our devices get even smaller and our processors start needing voltages that are even lower, will today's brilliant architecture be enough? Or is there a new revolution in power management waiting just around the corner, getting ready to change the world all over again?